Good morning, students. In last video we have seen what is a voltage source, what are two types of a voltage source, and also we have seen an ideal voltage source and a practical voltage source. So in this video we will see what is a current source and why it is needed. Okay, so let's start with the today's first point, current source. An electric current is defined as the rate of flow of electrons. In voltage source, this rate is not constant, but in some applications it is necessary to have a constant current that is given to the load, so the current source is used. So in voltage source the current is not constant but the voltage is constant, but where we need a constant current we have to use a current source instead of a voltage source. Independent current source is an energy source that pushes a constant flow of electrons through an electric circuit regardless of load presented to it. That means it do not depends on the load provided to it. The independent source has two types, ideal current source and a practical current source. We will see first what is the ideal current source and then we will go for the practical current source. Let's see the ideal current source. So this is the symbol of ideal current source. Is the label for the ideal current source. So this is the ideal current source which provides a constant current. Okay, and V is the voltage across this terminal. So the let's come to the graph. This is the graph of I versus V, and the current is constant over here. Okay, it provides a constant current. A straight line is shown over here. That means it provides a constant current. It delivers a constant current to the load no matter what amount of voltage appears across the current source. So here the voltage is less. If we increase the voltage, if we start going on an increase in voltage, there is no effect on the source current. The source current remains constant. Okay, now let's connect a load resistor over here. Is the current source and RL is the load resistor that is connected. So the value of V that is that appears across this load resistor is V is equals to Is into RL. Okay, the V is equals to Is, that is the current, multiplied the resistance RL. If RL increases, V also increases because it is directly proportional. So if RL increases, V also increases. So there is no limit on amount of voltage that appears across the source. That means there is no limit on the voltage that appears across this source, because this current source and this voltage source are connected in parallel. That's why same voltage, amount of voltage will appears across this current source also. So if RL increases, V also increases, and there is no limit on amount of voltage that appears across the source. So it can deliver any amount of voltage to the load. Now let's see the practical current source. In practical current source, there is a limitation on amount of voltage that can appear across the current source. Okay, so there is a limit on a voltage that can appear across this current source Is. That is, there is a limitation on amount of voltage that can be supplied to the load, because these two are connected in parallel. Okay, these two are connected in parallel. That's why. The practical source has a shunt resistor in parallel with the current source. In a previous case, in ideal one, there is no shunt resistor, but here in a practical current source, one parallel resistor is connected to this source, current source Is. So RSH is that current source. RSH is that shunt resistor, and ISH is the current flowing through this shunt resistor. Is is your supply current, RSH is shunt resistor, IL is the current flowing through the load, and we have connected a load resistor is equals to RL. Okay, now let's see what current we are getting at the output. So IL is the output current. So IL is equals to Is means this current, minus V upon RSH, or we can write it is ISH. The value of ISH is equals to V upon RSH. So IL is equals to Is minus ISH. IL is equals to Is minus ISH. Okay, the voltage drop across, we have to consider here the voltage drop across, we have to consider a current flowing through this shunt resistor also. Okay, the current is flowing through it. That's why there is a definite voltage drop over here. So IL is equals to IS minus V upon RSH, where IL is the current delivered to the load, IS is the supply current, V is the voltage appears across the load, and RSH is the shunt resistor. So let's see the graph. This is the graph of IL versus V, and this is your current source IS. So let's see what kind of current we are getting. If we are using an ideal current source, then we are getting a straight line. A straight line means there is no change in a current. So the current is not dependent on the voltage that appears across the current source. But here, if we increase the value of RL, if RL increases, V also increases, and let's see the changes. The current starts decreasing. This is the output of a practical source. Ideal current source has a straight line, and a practical current source, the current decreases as voltage increases or RL increases. As the voltage across the current source increases, the actual current flows through the load will decrease, because there is a leakage current through RSH. The current leakage is there across this. That's why IL decreases. So here IL is constant, here it is decreases. In previous case, IL is constant, that is equals to IS, but here IL is not equal to IS. It is less than IS because it is decreasing as V starts increasing. Okay, to reduce this leakage current, the value of shunt resistor should be high. Practically, the value of RSH is in the range of some mega ohms. So in a practical applications, we are not using the ideal voltage source or ideal current source. We are using ideal. We are not using ideal one. We are using a practical one, that is a practical voltage source and a practical current source. So now we will see what are the different kinds of signal waveforms we are using in electronics. So let's start with a waveform, the definition of a waveform. Firstly, what is waveform? So waveform is a graph of magnitude of a quantity with respect to time. So it is a graph of a quantity with respect to time. That quantity can be voltage, current, power, or any such a quantity. On x-axis, time is plotted. On a y-axis, voltage, current, power, etc. These quantities are plotted. Okay. Let's see the types of AC waveforms. The most familiar AC waveform is a sine wave, and there are some other waveforms also we used. Commonly used waveforms are a square wave, triangular wave, ramp wave, sawtooth wave. Some waveforms I have shown over here. So this is the sine waveform. This is the square kind of waveform. This is the triangular waveform. Okay. A waveform is a representation of how alternating current varies with time. Okay. It shows how an alternating current or any alternating quantity, say voltage, that varies with time, or the power is the alternating quantity that varies with time. So now we will see some terms related with the waveforms. So first term is a cycle. Let's see what is cycle. So I have shown here one sine wave. Okay. This is the positive half. This one is a negative half. This is positive half, that is in between 0 to pi, and this is a negative half, that is the negative portion. It is identical. These two halves are identical, but this is a positive one and this one is a negative one. That's only the difference. The negative half is from pi to 2 pi. So total cycle is of 360 degree or 2 pi radians, because it starts from 0 and ends it to 2 pi. Vm is the voltage shown over here. So I have taken a graph of V versus T. Okay. So this 0 to 2 pi portion is called as a time period, or it is called as a one cycle. So let's see what is a one cycle, the definition of one cycle. In AC waveform, a particular portion consisting of one positive and one negative part repeats many times. Means the same positive half repeats over here, again same negative, again same positive, negative, same positive, negative. Okay. In AC waveform, a particular portion consisting of one positive and a negative part repeats many times. Each repetition consisting of one positive and one identical negative part is called as one cycle of a waveform. That means one cycle consists of one positive half and one negative half. So a cycle is always of 360 degree, or in a radians we can say it is of 2 pi radians, because one half is of pi, another half is of pi. So pi plus pi is equals to 2 pi. So in a simple way you can remember a cycle consists of one positive half and one negative half. Okay, let's see the another term, time period T, or it is called as a periodic time. Okay, so it is defined as, once you understand the concept of cycle, it is very easy to understand the time period. It is defined as the time taken in seconds by a waveform of an AC quantity to complete one cycle. Okay, to complete this one cycle, what time the signal takes, that time is nothing but your time period or periodic time. After every t second, the cycle repeats itself. Suppose if the time is t second, then after t second, this cycle again repeats itself. After t second, this cycle again repeats itself. Okay. Now let's see the third parameter, frequency. The third term is a frequency. Frequency is defined as the number of cycles completed by alternating quantity in 1 second. Okay, how many cycles, how many such cycles a signal completes in a 1 second is called as a frequency. So it is defined as the number of cycles completed by alternating quantity in 1 second. It is denoted by F and its unit is cycles per second or hertz. So F is equals to cycles per second, that is equals to 1 upon T, and its unit is hertz. The next term is a wavelength. It relates the frequency of a sine wave with the speed of propagation. So wavelength term, it relates the frequency of sine wave with the speed of propagation. So wavelength is denoted by lambda. Wavelength is equals to propagation speed divided by frequency. So lambda is equals to c upon f, or we can give lambda is equals to c into t, because earlier we have seen f is equals to 1 upon t, or vice versa, t is equals to 1 upon f. The wavelength of a signal is depends on the medium. The wavelength is the distance between two identical adjacent points in a waveform. So this is the simple definition. Wavelength is the distance between two identical adjacent points in a waveform. This is important that the point should be adjacent. Okay, let's see the next term, phase. Okay, it specifies the location of a point within a wave cycle of repetitive waveform. Let's take one signal. This is the signal S of t. Okay, this is the signal S of t. A is the amplitude of the signal. The equation for this signal S of t is equals to A sine 2 pi ft. Okay, let's see, the signal has started from 0. Okay, the signal has started from the 0, so it has a 0 phase shift, and the equation given for this signal is A sine 2 pi ft. Let's see what is 90 degree phase shift. Okay, what is 90 degree phase shift? It is a plus 90 degree, it can be a minus 90 degree also. So see, compare these two signals. Here the signal has started from 0, but here the signal has started earlier to 0. Okay, the half portion is after 90, the half portion is before, the half portion is after 0 crossing point, and the half portion is before 0. Okay, so here the phase shift is of 90 degree, and the equation we can write, this equation we can write as a S of t is equals to A sine 2 pi ft plus 90. So 90 degree phase shift I have added into this equation. So here phi is equals to 90 degree. Phi is a phase of this sine wave. Okay, let's say the third case. Here the phase shift is equals to 180 degree. Here the cycle starts before 90 degree. Here the cycle starts before 180 degree. Okay, this is the 0 point. So before 0 point it had started 180 degree earlier. Okay, so here phase shift is equals to 180 degree, and the equation we can write S of t is equals to a sin 2 pi ft plus 180 degree. So this is the equation for it. S of t is equals to a sin 2 pi ft plus 180